Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Nura'in Nabilah binti Noranuar, Master Student under the supervision of Dr. Ahmad Kushairi and Dr. Sharidan Shafi'i from Universiti Teknologi Malaysia, together with Dr. Ilyas Khan from Majma'ah University. So today I will present on the unsteady free convection flow of water-based carbon nanotube due to non-coaxial rotation of moving disks. For our introduction, we'll be defined a few terms, which is heat transfer. So heat transfer is the process of transferring thermal energy from one place to another place in three ways, which is conduction, convection, and radiation. So actually, convection can be divided into three, which is free convection, forced, and mixed convection. So in our study, we will deal with the free convection flow. So free convection can be defined as the fluid motion is induced because of the variation density axis in some regions of the fluid, and basically this convection is not generated by any external sources. So the main driving force for this convection is the gravity. So for nanofluid is a mixture of the dispersion nanoparticle into conventional base fluid. So for nanoparticle, it can be from metal oxide or carbon. Conventional basic can be from water, oil, and ethylene glycol. So basically, conventional base fluid is found to have a limited capability in transferring heat because they have a low thermal conductivity. So this nanoparticle is added to this base fluid because we want to enhance the thermal conductivity so that the heat transfer can be more effective. And rotating system. Rotating is circular movement of a body around a center or point of rotation, and inside the rotating we have the Coriolis force. If this force will be affected how the fluid will be flow. So for the moving disc, the disc will start to move and rotate so that the fluid can be enhanced. So here our rotating will be involved on non-coaxial rotating. So mathematical formulations. So here the moving disc is chosen to be in the x-axis direction. So in our study, the medium will be filled with the nanofluids, which is the combination of the water in the either single wall or multi-wall carbon nanotube. And we have the two axes of rotation. So we achieve initially when t is equal to 0, both disc and fluid will rotate at the z prime axis. When t is greater than 0, the disc will move into the z axis and rotate here, while the fluid will remain on this axis, z prime axis, and rotate here. And then we have the thermal boundary layer and momentum boundary layer, which is we will come up with two governing equations, which is momentum and energy equation. So momentum will be formed like this. So here is the term that will be considered as the rotating term. So here is the heat transfer effect. So since our problem is involved in the rotation system, so our velocity at the last solutions will be introduced in the term of complex velocity, which is like this. So for the small f, it will be for the real part, and g is the imaginary part. So real part will be describe the primary velocity, and imaginary will be describe the secondary velocity. So for energy equation is like this. So here, since we are considering the nanofluid fluid model, so here the thermophysical property will be used based on the particular nanofluid that we use. And then after that, this governing equation is completed with the initial condition and boundary condition like this. So since we are consider our problem is in moving disc, so this type of boundary condition will be considered. And then for others condition, will be take it from we will refer by the previous study that has been published of this condition. And here is the dimensionless process. So when we solve our problem, actually there exists the units in our calculation. So this unit actually we want to cancel out this because we only want the certain constant parameter to be appeared. So in order to cancel out this, we use the dimensionless process. So first we introduce the dimensionless variables like this. So this variable will be substituted into the governing equation. so that the dimensional system will be converted into the dimensionless form, which is this momentum and energy equation together with the inertial and boundary condition in the dimensionless form. So here is the constant parameter that appeared in our study, where it defined as like this, where PR is the Prandtl number, GR is the Grashof number, U is the amplitude of this, P is nanoparticle volume fraction. So actually this constant parameter will be used in order to investigate later the physical behavior of the velocity and temperature profile. And then Laplace transformation method we use in order to solve this governing equation. We use Laplace transformation method. Why we use this method? Because our problem is considered to be unsteady. So this means that our involves the variation of t. So by using this method, we can convert the domain of t into a new domain so that our solution can be easily handled. And then after taking the Laplace transformation, the momentum and energy equation is formed like this, together with the boundary conditions and also energy and also boundary conditions. So here we can see after we taking Laplace transformation method, so our momentum and energy equation will be in the form of the PDE here. And then so in order to solve this equation, this boundary condition will be substituted into this equation, and we get the resulting solution, but still in the Laplace transformation, but still in the Laplace form. So here, in order, since we want that our velocity is in the form of the fzt, which is in the t domain, so we use the inverse Laplace transformation in order to convert back our proposed new domain before into the original domain, which is t. So after the inverse Laplace, we got the velocity solution in the form like this. So here has that t together with their f1, f2, f3 and other antecedents which defined as this, and also f4, f5, f6. So same goes to the temperature solutions. Also we get in this form. And then here is the constant parameter that appeared in our study, which defined here. And then for our results and discussion. So in order to know whether our solution is correct, so by two methods, which is we have to ensure that our physical character, our physical velocity and temperature is satisfied of the embedded parameter, of the effect of embedded parameter. So another way is we check our initial and boundary condition, whether our graph is satisfied or not. So here this figure shows that the primary velocity, secondary and temperature profile under the effect of P. So when P increase, velocity also increase, and same goes to temperature. When P increase, temperature also increase. This is because why temperature increase? Because when P is increased, this means that the thermal conductivity also increase. So the nanofluid with the higher thermal conductivity, actually they can conduct more heat. So that's why the temperature will also increase. And here we can see that the boundary condition, this graph is satisfied the boundary condition that has been proposed before. So then for the impact of T on temperature profile, so increase of T will show the increasing of velocity. Same goes to temperature, increase temperature with the increasing of T. And also satisfied the boundary conditions. So then the impact of Grashof number on the velocity. So increase of the Grashof number will increase also the velocity. So why? Because the Grashof number is defined as the ratio of the buoyancy force and the viscous force. So when GR is increased, this means that our buoyancy force in this fluid will be increased and the viscous force also decreased. So with this great buoyancy force, the flow will be enhanced, which means that the velocity will be increased. And here also this graph also satisfied the boundary condition. And also we U increase and the velocity also increase, satisfied boundary conditions. And here another way we want to check whether our solution is correct is by comparing our present result to the published result. So here we compared with the Muhammad ETAL. So in this published result, we're letting the omega equal to 0 since our problem is not involve the omega. And the present solution is we let the phi is equal to 0 because the published result is not involve the nanofleet model. So when compared with both solution, it shows that the present result is found to be identical with the published. Same goes to secondary solution also. So this means that our solution is correct. And then so our conclusion, the unsteady free convection flow of water-based carbon nanotube due to non-coaxial of moving D has been investigated. The dimensional momentum and energy equation, together with the inertial and boundary conditions, are converted into non-dimensional form by using non-dimensional variables. And the exact solution is obtained by using Laplace transformation method. The velocity and temperature profile with the effects of the phi, t, gr, and u are graphically plotted and analyzed in detail. So here in the summary of our result, so when phi, t, gr, and u increase, both of these are increase the velocity profile. And for the temperature, when when t and phi increase, also temperature increase. And here I forgot to explain the result. So when we see the result, actually the comparison of single wall and multi-wall. So in the temperature, you can see that single wall profile is higher than multi-wall because single wall has higher thermal conductivity compared to multi-wall. So that means that single wall can conduct more heat. For the velocity profile, it can be seen that multi-wall have the higher velocity compared to single wall because the multi-wall have the less density, low density, so that's why the velocity is increased. And lastly, our result is verified by the Muhammad ETL and is identically found. It means that having the excellent agreement. And here is the reference that has been used for our study. And so here is the financial support to our study. And lastly, that's all from me. Thank you.